so picking up where we left off, we had this idea, right? We switched our variables in our integral, and we ended up with a new region S, and we changed x to g of uv and y to h of uv, and we added in a factor of the absolute value of the Jacobian, where that expression is going to be in terms of u and v, and then we do this du dv. So this is the Jacobian of x, y with respect to u, v. So we're kind of keeping track of it. Was a dx dy integral, now it's a du dv integral. What's really happening geometrically is this is going back and forth between a region R, where R is in the xy plane, to a region S, where S is in the UV plane, because we are switching to new coordinates. Now, we need both of those to be simple regions, meaning we can describe them. So, what we mean though simply is they're literally both going to be simple either vertically or horizontally. And then the mapping that we're using is by mapping x is g of uv and y is h of uv, which really means that my mapping is t from s to r. So we're taking t of a coordinate point uv, and we're outputting then the coordinate point g of uv, h of uv. So that would really convert over to an xy coordinate then. We do need g and h to have those continuous first partials so that the Jacobian is well defined. And then we need t to be 1-to-1. Possibly it cannot be 1-to-1 on the boundaries, so 1-to-1 being injective. So basically that means that otherwise we want to be able to try and trace back, go backwards in the process as well. So thinking about what that looks like then, oftentimes the goal of these change of variables is to simplify our region, right? When we think about when we converted to polar coordinates, this was often our goal, was simplifying the region R. Sometimes we do want to do it to simplify an integrand, that's okay too. But I want to focus on that idea of simplifying the region. So let's use polar coordinates as an example. We often switched to polar coordinates anytime my regions were fairly circular in nature, right? If I try to describe this region in rectangular coordinates, it's fairly challenging. I've got two different kind of linear curves and two different curves that would be related to equations of circles. It may or may not be able to be described in a single region. I might have to split it up into multiple regions. So it's not simple to describe in terms of x and y coordinates. However, it is simple to describe in terms of polar coordinates, where in this case, remember, we would have the x is represented by r cosine theta and y is r sine theta. So we're making those change of variables. And then if we think about how to represent this, right, we've got r just goes from a to b. And then we've got theta goes from alpha to beta. So if I literally plot that region in the r theta plane, so not an xy plane anymore, but an r theta plane, well then literally r goes from a to b, and then theta goes from alpha to beta, whatever those are. And what we end up with is just a rectangular region. So we end up with a very simple region. So we're literally going from a constant to a constant, and then another constant to another constant. So we very much simplified our bounds for our region by doing this conversion. This is kind of the whole goal. Now, there are going to be other instances where we're going to create functions like for y and x for different purposes, where we can essentially say that I'm trying to go from like one type of curve to another similar type of curve. And we'll see some examples of that. But I want to check here, what is the Jacobian if we do a switch to polar coordinates? We probably should have an idea already of what we think it should be because we've done switches to polar coordinates, but let's confirm our suspicions. So if we do this, we'll have, right, that partial of xy with respect to uv, which in this case would be r theta. So this is the Jacobian of xy with respect to r theta. So we're going to do the determinant. Remember, we do this in case, we'll end up with dx dr and then dx d theta, where both of those are partial derivatives. And then we'll have the partial of y with respect to r and the partial of y with respect to theta. So we're doing those variables in order, right? We went from x, y, so x is on first row, y is on second row, to r theta, so r is in first column, theta is in second column. So let's write in what those are. So if we do the partial of x with respect to r, so r is my variable that we're gonna take a derivative with respect to. So then the derivative of r times a constant would just stay the constant, so we'll get a cosine theta. And then the partial of x with respect to theta, now we keep r as a constant. The derivative of cosine theta will be negative sine theta, so we're going to get negative r sine theta. And then the partial of y with respect to r will be sine theta. And then we're going to get the partial of y with respect to theta is we'll keep the r, and then the derivative of sine theta is cosine theta. So we've got r cosine theta. So then we need to simplify that determinant. So we've got r times, so we've got cosine theta times r cosine theta will be r cosine squared theta. And then we've got minus negative r sine theta times sine theta, which really turns into plus r sine squared theta. And if we take a look at that, we've got a cosine squared theta plus a cosine squared theta with the same coefficient out front. So if we were to factor that r out, cosine squared theta plus sine squared theta is 1, so this just gives me r. So then remember, inside the integrand, my scaled factor is we use the absolute value of that. So we would do the absolute value of r, which so long as r is non-negative, would just be r. So we can always just restrict ourselves to r being non-negative when we do this conversion. If it was negative values, then we would convert them over to positive values there. But that's why we have the r dr d theta when we switch to polar coordinates, because it is the Jacobian. What we're going to take a look at in our next examples is, what about some other change of variables where we're going to create the change on our own rather than converting to something established like polar coordinates? How can I just take a look at a region that, well, as is, it's kind of a little messy, a little complicated, but I can recognize that, oh, well, if I made this substitution, it would simplify to a very simple region. That's what we're going to do next.